Hey there, everyone. Ryan Schul, Straight Data Science. So, in the project today, I want to talk about how to predict when a product will fail and how can we address that? How can we be proactive about that and manage that a little bit better, right? When we can predict when a project will fail, we can do preventative maintenance, right? And that is extremely valuable across many industries, especially manufacturing, but whatever. You can be more proactive, more productive, and make more intelligent decisions and ultimately save the business money, right? So this does a bunch of different things, minimizes downtime, reduces maintenance costs, preventive intervention, prevents catastrophic events, improve product design, enhance customer satisfaction. That's a big one, right? Optimize inventory, support warranty planning, boost safety, right? And enhance people's awareness, right? And improves overall ROI, which translates to your bottom line earnings, right? So let us go ahead and jump into it. So I couldn't find any data that I really wanted to online, so I created my own. This is just dynamic data creation, but it's pretty realistic, and I think it will illustrate the point. So we have a few different devices or widgets or whatever you want to call it. I'm going to run the process right here and create some sample data. So we're going to have 1,000 rows of data. We have product names, so we know what this item is. Usage intensity, environmental temperature, that can have an impact on how long the product or the thing, what is it called, like a screw, nut, bolt, whatever, how long it's going to last, humidity level, and then time to failure. And we know this from historical examples. We know like how long a nut is going to last before it wears out. We know how long a bolt is going to last before it breaks or before it loosens, right? We know this from historical examples. And you need that history. If you just are doing this for the first time ever and you put a screw into a I don't know, a forklift or something, whatever, right? Pick whatever you want. And it's the first time doing that. You don't know how long it's going to last. But historically, if you capture this data and you preserve that, you can do analysis on this. So the first time you do it, yeah, maybe you're not going to know. But if you have a few years of experience and you've seen before what's happened in the past, you can make predictions into the future and understand what's going to happen next, right? So the time to failure is what we're trying to predict. That's the y variable. The x variables are the inputs. So this is the independent, x is independent feature, well, the y is a dependent. We're always trying to predict the y, right? I've got several videos on my channel about this. I don't even know how many, dozens on the channel at this point. So we're trying to predict the y and we use the x to predict the y. And if you think about it, it's like anything. Like if you're trying to predict the weather tomorrow, it could be a couple of things. You can predict the temperature or like is it going to be hot or cold? Is it going to be sunny or cloudy? Is it going to be windy or no wind at all, right? There's different ways to predict the temperature. And it's all based on historical events. Like what time of the year is it? Where are you located geographically? Things like that, right? So we're trying to predict the outcome here. This is the time to failure. Okay, so let me hit Control Enter right here. And this is going to be a pretty short video, guys. It's not going to be a big one. R squared is 0.97. So that's pretty decent. That's what we want. High nines, 0.95, 96, 97, 98, 99. That's great. 1.0 is perfect prediction. That doesn't really happen in the real world. If you see that, I would be very suspicious. I would say the model is probably overfitting or your analysis is incorrect or something like that. Like something might be off. You can't predict with 100% precision what the outcome is of anything because it's always changes. There's always something that you don't expect, right? And that's called life. That's life, right? So you try to make the best predictions you can, but you're never going to be 100% accurate. But 0.97 is very, very good. So I'm very happy with this. I'm very satisfied. This is the usage intensity and the time to failure right here. So we're looking at the correlations of these on the axis. It's always 1.0, right? So time to failure and the usage intensity is negatively correlated. If you think about that, that totally makes sense, right? The more you do something, then the faster it's going to fail. If you have a car that you drive and you have 100,000 miles per year on a car, the car is not going to last as long as somebody that drives 5,000 miles per year, right? So as the usage increases, the time to failure decreases, right? It's going to happen sooner and sooner as you use it more and more. So I think this totally makes sense. Let me refresh this cell, and this looks like, wait, let me save this thing actually and refresh this because something is not being displayed correctly, and that's fine. In these Jupyter notebooks, these things are pretty sturdy, but they can be a little bit delicate too. So, okay, so we have this. Okay, let me print this out. I can do this a little bit different. I like this one. Was playing around with this thing earlier. Okay, so we know how much the product is being used, and the more usage you get out of it, the shorter the lifetime of the product, right? So we have the product name, usage intensity. That's what we started with. Humidity level, time to failure. That's how we started, right? Humidity level. Actual time to failure is over here, and this could be any unit you want. So it's kind of generic. I'm just giving you like a generic example here. This could be hours. This could be minutes. I don't think realistically it's minutes. This could be hours if something is being used very, very, very frequently in a very intense environment. Probably days, right? I didn't name the actual like duration of time in days or hours or even years. Maybe this is 300 years. It's probably 300 days. But again, it depends on your example. I'm just trying to illustrate the point here, right? And then predicted time to failure. So these should be pretty close. So 313, let's call it days, 333 days, predicted time to failure, actual time to failure. So this product failed like 10 days or no, 20 days a little bit early. This one is pretty close, 275, 272, right? 243, 240. So it's off by 2 days. This is 3, 197, 92. It's off by 5, 315, 293. So that is 15 plus 7, whatever that is, 23 or something like that, right? So we're pretty close, and that's why we have the high R squared right here. So 97% of time, we're going to be correct, but we're going to be off a little bit, right? But the whole point of this exercise is to say, like, how long do we expect this part or this product or this type of manufacturing item, how long is it going to last on average? And then how do we do the replacement and be productive and be proactive too, and replace the part before it actually wears out, because that's going to help us be more efficient, more effective, help the bottom line, help the ROI, which is return on income, right? So it helps all of these things. So if I run this new product, we can actually predict based on these items over here, these features over here, based on usage intensity, environmental temperature, and humidity level, we can predict when this item is going to fail. So this is one single item right here. We can have a batch process. We can load an Excel spreadsheet into the model. Once it's been trained and tested, we can make a prediction on all of these items. We made a prediction on a whole bunch of items over here. This is one single prediction at a time. I've got several videos on my channel about this. So you create the model, you train it, you test it, and then you use that to make a prediction. And in this case, if these are the variables based on usage intensity, okay, and environmental temperature and humidity level, this product is expected to last, I think I said days. Again, I didn't really um, determine the unit of measurement here or really define it, but the predicted time to failure is, let's say, 234 days. So this item is going to last 234 days. If you decrease the temperature maybe 20 and humidity level is maybe, that would be probably lower, a lower temperature, the predicted time to failure goes from 234.7 to 300. So it actually lasts longer, right? So this product, whatever this is, this item lasts longer if the temperature is lower, right? It's actually freezing temperature. So maybe this is some type of refrigeration part. This is what the model does, right? You train it and test it based on the product name and the usage intensity and these other features that you feed into the model. The model is going to do a statistical analysis and say, okay, generally, I know how long this part is going to last in this part and this part and this part and all these different infrastructure parts. I know how long it's supposed to last on average, and I can make a prediction into the future into how long that part is going to last. And remember, we got 97% accuracy, so it's very accurate. So I want to show you one more graphical analysis here just to illustrate the point again, because I think a picture is worth 1,000 words. And you can see all the data is pretty tight. The regression line is negatively trending down from the northwest to the southeast of this chart, and it's going down to the right. I want to add one thing. I like to make this and rerun it. So a lot of times you'll see like an upward sloping regression line. You see it all the time in school. I saw it all the time in all my classes. So it's only upward sloping. So that's a positive correlation, right? It's called positive correlation. Usually it's upward sloping, but in different industries or different sectors or different businesses, it could be negative, right? And that's totally fine. As usage as usage intensity increases, the time to failure decreases, right? So that's why we have a negative sloping regression line here. And you can see all the points around the regression line are pretty tight, right? Everything here is an outcome based on this data over here, right? And you have a negative sloping regression line, which looks a little bit weird. You don't see this a lot in academics, but in the real world, like all bets are off, right? It could be anything. And this is totally fine in the real world. Usage intensity increases, like I said about that car. You drive that thing 100,000 miles per year, the car's not going to last as long as another car that's been driven 5,000 miles per year. You increase the usage, and the lifespan of that vehicle decreases. You decrease the usage, and the lifespan increases, right? So you have a negative correlation here, and that's the way it is. That's totally fine. That's the way these things work right here. So this means products that are used more or more intensely tend to fail sooner, right? So that's just common sense. So I think the regression line looks a little bit weird if you use the academics and normal statistics, but this does exactly what it's supposed to do. So the upward sloping positive correlation is like kind of like, okay, if you make more money, your stock price increases, right? That's a positive correlation. This is negative correlation, but it's a whole different concept. So you have to get your mind around that and understand the use case here in the scenario that we're doing here. So that's pretty much it. I think we did this pretty well. I'm going to wrap it up. I have another video on my channel that's somewhat related to this. I try to mix them up a little bit, try to make it different. I don't want to duplicate efforts and like create the same kind of scenario over and over. I don't believe in that. I think that's nonsense. I think it's useless. But I do have another video that's a little bit similar to this. I think this topic is interesting. Predicting when a product will fail based on historical failures and the historical data that you've collected in the past. We can make predictions into the future, what's going to happen next. Okay, so that's pretty much it. I'm going to wrap it up. Thanks for your attention today. Thanks for tuning in. Thanks for coming here, and hopefully this is educational and somewhat inspirational. And I will see you guys in the next one. Take care. Bye.